Welcome back to chapter 21. We're going to finish it up. This part of the chapter is relatively short, but important. So let's talk about terminal voltage. If you were trying to test your car battery to see if it was good, you might take a voltmeter and connect it across the two terminals on the battery to get a reading. Hopefully you end up with a reading that tells you it still has 12 volts to offer. Or if you were testing batteries in a flashlight, you might put them on a voltmeter or a battery tester, which is the same thing, to see what kind of terminal voltage you have. So with batteries, all voltage sources have a source of electric energy, but they also have an internal resistance. You can't have electricity flowing through a circuit without some sort of resistance to that flow. So the voltage source will exert forces on your electrons and that causes them to move. But again, there's a resistance to this motion. So the excuse me, the EMF, or the electromotive force, is that potential difference when there's no current flowing, and we measure it in volts. Now, as we scroll down, let's look at the differences between battery types. So suppose you have a 12-volt truck battery and a 12-volt motorcycle battery. They are vastly different in sizes. Truck batteries are larger, motorcycle batteries are smaller. They both have a 12-volt EMF, but the truck battery is able to deliver a larger current, so it's going to have a smaller internal resistance than the motorcycle battery. Why is that? Well, automobiles in general have more things that need current right away, just at the moment they're turned on, than things like motorcycles do. So for any battery, your terminal voltage will equal the EMF minus the current multiplied by the internal resistance. You don't need to memorize this formula. I just wanted you to see where the numbers are coming from that we'll talk about. So if you look at a car or a truck, it's going to act like a large resistor. And again, remember, you've got the radio and the headlights and all kinds of things going on. The backup camera these days. So V is equal to IR. The terminal voltage has to equal the current multiplied by the total resistance load. And we've said before that things like automobiles have a larger resistance than things like motorcycles do. So if we plug all of this in, you can see that this internal resistance, this little r, shows up in the denominator if we're trying to solve for the current. And what that tells us is that if you want a large current, you need to have a smaller internal resistance. So how about multiple batteries? Normally in a car or a motorcycle, there's one battery, although there are exceptions to this, but we won't go into it. But there are a lot of devices that use 2 or more batteries. If you've got a scientific calculator, it has 4 batteries in it. A large flashlight probably has anywhere from 2 to 4 batteries. So it just depends on the device. The batteries will act like resistors when they're wired in series, and that means that they're going to have an internal resistance that adds and an EMF, remember that's another name for the voltage, that adds. So if you look at a AA battery, because we seem to use a lot of those in our lives, they have an internal resistance of 0.15 ohms all the way to maybe 0.1 ohms. When your battery gets old, this internal resistance actually increases. And that's why sometimes your battery doesn't work as well as it used to. It doesn't provide enough current in order to energize the device you want to run. So if two batteries are wired in parallel, this voltage or EMF is the same as one of the batteries would be, because if you think back to parallel circuits at the start of the chapter, the V total equals V1 equals V2 when you wire them in parallel. So in parallel, the voltage or the EMF is going to be the same as the individual ones, but the resistance actually decreases when you wire them in parallel. And if you decrease your resistance, that's going to increase the available current. As an example, to maybe make this a little easier to understand, let's consider four batteries. We'll take four AA batteries, each one 1.5 volts, and they'll have an internal resistance of 0.1 ohms. And let's connect them in series and compare our numbers. So in series, the voltages add. So 1.5 plus 1.5 plus 1.5 plus 1.5 gives you 6 volts. The resistances add. So those internal resistances, 4 batteries, each one at 0.1 ohms gives us 0.4 ohms. And the current is going to be V divided by R. So 6 volts divided by 0.4 ohms, which will give you 15 amps. Now see what happens if you wire them in parallel. Our V total is not 6 volts. Our V total is just 1.5 volts. But look what happens to the total resistance. In series, it was 0.4 ohms. If you wire them in parallel, it's 0.025 ohms, considerably smaller. And then finally, let's look at the current. In series, the current was only 15 amps. If you wire them in parallel, the current is 60 amps. So big difference. So our obvious conclusion is that if you need a lot of current, it's better off to wire those batteries in parallel. So why do we have batteries in different sizes? You may never have wondered about that. You've got button batteries and AAAs and AA's and C's and D's. They even make 4A batteries and B cell batteries, all kinds of different sizes. What most people don't realize is that the standard small cylindrical shaped batteries, so the AAA, the AA, the C, and the D, all are 1.5 volts. But the larger the battery, the longer it's going to last. A typical AA battery is going to last twice as long as a AAA battery. So why would you use AAAs if they use up faster? Well, you use them when you need things to be lightweight. So typically size dictates a smaller battery. But if size is not a concern, if it's okay if something is large and heavier, then the bigger batteries, the C and the D cell, are probably the better bet because they'll last longer in that situation. All right, animals and electrical detectors. So our last little topic, some animals can detect electric charge. Fish and sharks are notable for this. An electric eel can produce its own EMF, so its own voltage. They have organs called electroplaques in their bodies, and they act like the cells in a battery. So each one of them has a voltage of 0.15 volts. So small eel, not so dangerous, but there's a variety of South American eel that'll have 140 rows of these electroplaques for 5,000 total, and it can produce a potential of 600 volts with a current of an amp, and that is enough to kill you. So I guess the moral of the story is stay away from those South American eels. Now, you can detect electric charge. You may have noticed that if you get close to something that has a static charge built up on it, the hair on your arm might stand up. So you have a little bit of a sense of that. We just are not nearly as good as some other animals. All right, last topic, Kirchhoff's rules. So Kirchhoff's rules are used when you have those combination series parallel circuits, and it's a way to calculate the individual currents and voltages through each little section of the circuit. We are not going to go over them, but if for some reason you are curious about it, your textbook has a whole section on it. You are more than welcome to look at it. And if you have individual questions, I'm happy to help you. So this stops our chapter 21. So we will make a little note and stop the share and stop the recording.